Hello everyone, I'm going to talk about quantum correlations in time. We investigate quantum correlations in time in different approaches, including indefinite causal structures, consistent histories, generalized signaling games, out-of-time order correlations, path integrals, and pseudo-density matrices. We establish close relationships among these spacetime approaches in non-relativistic quantum theory, resulting in a unified picture, except the path integral approach. The motivation came from the notorious problem of time in quantum theory, because time cannot be treated as an operator in contrast with space. Several attempts have been proposed to incorporate time into the quantum world in a more even-handed way to space, including indefinite causal structures, consistent histories, generalized quantum games, spatial temporal correlations, path integrals, and pseudo-density matrices. Different approaches have their own advantages. Of particular interest here is the pseudo-density matrix approach. One advantage is that quantum correlations in space and time are treated on an equal footing. Here, we assume that temporal correlations should be treated as an even-handed manner as spatial correlations. We achieve an understanding of how the different approaches connect to each other by comparing temporal correlations with pseudo-density matrices. The pseudo-density matrix formalism aims to treat space and time on an equal footing. In general, this formalism defines an event by making a measurement in space-time and is built upon correlations from measurement results. Thus, it treats temporal correlations just as spatial correlations from observation of measurements, and unifies temporal correlation and spatial correlation in a single framework. As a price to pay, the space-time states represented by the pseudo-density matrices may not be positive semi-definite. As the blue block, an n-qubit density matrix can be expanded by Pauli operators in terms of Pauli correlations. In space-time, instead of considering n qubits, let us pick up n events. For each event, a single qubit Pauli operator is measured. We redefine the correlation part as the expectation value of the product of the results of these measurements. Then the pseudo-density matrix is defined. Similarly to a density matrix, a pseudo-density matrix is Hermitian and unit trace. But it is not positive semi-definite as we mentioned before. If the measurement is space-like separated or local system evolve independently, the pseudo-density matrix will reduce to a standard density matrix. Otherwise, for example, if the measurements are made in time, the pseudo-density matrix may have negative eigenvalues. Now we started to investigate quantum correlation in time in different approaches. The concept of indefinite causal structures is proposed as probabilistical theories with non-fixed causal structures as a possible approach to quantum gravity. The process metric formalism is one of the indefinite causal structures, assuming local quantum mechanics and well-defined probabilities. We analyze correlations in both the process matrix formalism and the pseudo-density matrix formalism. We take a case with normal causal order and map correlations in the two formalisms into each other. Then we consider the set of all possible causal correlations forms a causal polytope. The phases of the causal polytope are defined as causal inequalities, and they are violated in the true formalism with indefinite causal structures. We also discussed the connection between the two formalism under post-selection. Thus, it is possible to map a process matrix to a corresponding pseudo-density matrix under correlations in 3 different ways. Consistent histories or decoherent histories is an interpretation for quantum theory. The main idea is that a history, understood as a sequence of events at successive times, has a consistent probability with other histories in a closed system. The probabilities assigned to histories satisfy the consistency condition to avoid the interference between different histories, and that set of history are called consistent histories. In consistent histories, probabilities are assigned to histories when the decoherence functional is diagonal, and the diagonal elements of the decoherence functional are the probabilities for the histories. It is also the probabilities in temporal correlations of pseudo-density matrices. A non-local game is a kind of interactive proof system with only one round and at least 2 players play in cooperation against the referee. In quantum classical non-local games, the questions are quantum rather than classical. In quantum classical signaling games, instead of 2 players, Alice and Bob, we consider only 1 player, Abby, at 2 times. Then the probability in a quantum classical signaling games with a trivial input at the later time corresponds to the probability in a pseudo-density matrix with quantum channels as measurements. Out-of-time order correlations can be represented as temporal correlations in pseudo-density matrix with half the number of steps for calculation. For example, a 4-point out-of-time order correlation, usually calculated by evolving forwards and backwards twice, is represented by a tripartite pseudo-density matrix with only once evolving forwards and backwards. In general, temporal correlations in path integrals do not have the operational meaning as those in pseudo-density matrices, since they use different measures. The path integral approach defines temporal correlations differently, weighted by amplitudes rather than probabilities. However, the path integral representation for spacetime states and decoherence functional are still consistent due to the consistency conditions. So far, we found several mapping and relation among these approaches, including, first, we map process metrics to pseudo-density matrices in 3 different ways. Second, we show the diagonal term of decoherence functional in consistent histories is the probability in temporal correlations of corresponding pseudo-density matrices. Third, we show quantum classical signaling games have the same probabilities under quantum strategies as temporal correlations measured in the pseudo-density matrices. Fourth, the number of steps in calculating out-of-time order correlations is halved by using pseudo-density matrices. Fifth, correlation in path integrals are defined as the expectation value in terms of the amplitude measure rather than the probability measure. Thus, they are different from all the other correlations. We conclude that under this comparison of quantum correlations in time, the different approaches, except path integrals, are closely related. We hope that these relationships can further add a flow of ideas between the different approaches. How to move on to relativistic quantum information or further to quantum gravity is still a big gap. gap worth exploring. That's all. Thank you for your attention.